Next, let's take a look at the action potential as it appears on a voltage meter in comparison to what's happening with the sodium and the potassium ion channels. So on this slide, the graph is showing us the action potential on the voltage meter across time. Again, time is passing by on the x-axis. Now notice, we are in milliseconds here. We are in a fraction of a second this action potential is occurring. On the x-axis, we're looking at voltage and we're looking at millivolts. Again, we start off at resting, which is about minus 60 millivolts. Now, over here, you can look at a little piece of membrane. You can just see the heads and the tails and the heads. And then we've got these two proteins embedded in the membrane. One of them is the sodium channel, one of them is the potassium channel. And you can see that at the beginning of this, they're both closed. We're at rest. Now, the other thing that they're showing us on this graph is this purple region right here. This is going to show us where the action potential is beginning in terms of depolarization, but it's leading us into refractory periods. Remember, we said there are two refractory periods that are going to be important in terms of preventing what you could think of as overstimulation of the neuron. You can also see threshold potential and things like that on this graph. We'll talk about all of it. So we're going to walk through this action potential in relation to the ion channels over the next couple of slides. We're starting off at rest. We're at minus 60 millivolts. The neuron is at rest. The sodium and the potassium channels are closed. Now, we're going to apply a stimulus to this neuron. Its dendrite is going to pick up some kind of information. And that information can come in many different forms, depending on where that neuron lies. If it's a sensory neuron, it could be picking up any kind of sensory information, from sound to light to pressure to pain, any kind of sensory information. If it's on the motor side, it's picking up electrical information from the central nervous system, and it's carrying it out into the periphery to elicit an effect. So, in order for the stimulus, which is being applied right at the start of this dark purple region, in order for it to be effective, it has to be at least plus 20 millivolts. So we're going up, plus 20. We're going up here until we hit minus 40. This is threshold. As long as we hit minus 40, as long as the stimulus is big enough, we can enter into depolarization. Remember, depolarization moves membrane potential very rapidly into the positive, away from resting. Sodium channels are going to help cause this depolarization. On this slide, we're looking at the next moment. We've reached the minus 40 mark. We've hit threshold potential. Sodium channels are going to open. Sodium is going to rush into the cell, making the inside of the cell more positive, less negative. That's happening right here. This is depolarization, and it will continue until the membrane potential hits plus 40. So we moved from minus 40 threshold potential in the positive direction up to plus 40 during depolarization. Now, plus 40 is another critical voltage. On this slide, we're looking at the next moment in time. When we hit that plus 40 mark, what will happen is the sodium channels will close and inactivate. That's what the little lock is showing us. So not only have they closed, but they've been inactivated. At the same time, at that plus 40 mark, the potassium channels are going to open. Potassium is going to flow out of the cell, taking its positive charge with it. That's going to make the inside of the cell more negative, and we're going to start repolarization. As more and more and more potassium flows out, we're going to repolarize. We're going to head back down to resting. This is where, once you hit resting, this is where hyperpolarization is going to occur. Remember, we said hyperpolarization is the process that takes us below resting. This is also what people refer to as the undershoot. So we're heading back to resting, but we head a little too hard because we're actually going to pass by resting and go even lower. But then we'll come back up to resting and we'll be back. In hyperpolarization, what's happening is the potassium is just continuing to go out through its channel past the resting potential mark, because you have to hit minus 75 millivolts for the potassium channels to close. Now, what causes the return to resting after this happens is not an opening of the sodium channels or anything like that. It's that passive flow of ions that returns us back to resting. So this event right here, that's very slow, that's through a passive sort of leakage of ions that brings us back to resting potential. On this slide, we're looking at that moment again when the sodium channels are closed and inactivated, the potassium channels are open, and we've gone down from plus 40, past minus 40, past minus 60 into the undershoot. This is hyperpolarization, and it won't be until we hit about minus 75 that the potassium channels are going to close. Now let's think about these refractory periods. These are periods of activity where action potentials cannot be regenerated. Now, what does that mean? When you think about an action potential, the purpose of the action potential is to transmit signal across time. We're sending signal along the length of the axon over time, over milliseconds of time. If a neuron gets re-stimulated during this process, you could interrupt this process. So the cell takes effort to prevent that from happening. Now, there will be a time during the action potential where we're in an absolute refractory period. And what that means is the sodium channels are not only closed, but they are inactivated. In other words, no amount of new stimulus can open those channels back up. This is where we're really seeing the difference between a closed ion channel and an inactivated ion channel. A closed channel can be opened if the right voltage is hit. but an inactivated channel, it can't be. A closed channel could be reopened if the stimulus was plus 20 or more, but an inactivated channel can't. So that's what we call the absolute refractory period, the time when the sodium channels are not just closed, but they're inactivated. The relative refractory period comes next. During the relative refractory period, the inactivation particles are going to start to drop away. In other words, they're going to open back up that entrance to the ion channel, but they don't all reactivate at the same time. Reactivation is sort of a slower and more uneven process. And while sodium channels are reactivating in this sort of uneven way, the potassium channels are still open. So when we add those things together, during the relative refractory period, a new action potential could be generated, but it requires an extra strong stimulus to do it. If we go back and look at our graph, up at the top here, they're showing us the absolute refractory period and the relative refractory period. So these are periods of time here. During the absolute refractory period, no new action potential can be generated on this neuron, regardless of how big the stimulus is. It is refractory to a new action potential being generated. Absolutely. The relative refractory period is different. During the relative refractory period, sodium channels are beginning to reactivate. Some of them are going to have their inactivation particles moving out of the way. Some of them not yet. Potassium channels are still open, and a new action potential could be generated during this time period if the stimulus was big enough, was great enough. Now that leads us into this idea of how action potentials get transmitted. Remember, the idea of an action potential is that the neuron is sending it along the length of its membrane in the direction of down the axon. The electrical current, the signal, is being sent down the axon so that it can then be transmitted to the next cell in the pathway, whether it's the pathway towards the central nervous system or the pathway away from the central nervous system. But the idea is we need it to travel in one direction. Now, when it comes to transmitting the signal, there are two ways that that signal can travel. It can travel passively, and it can travel in an active way, in a way called propagation. So we're going to talk about the passive spread of electrical current in the membrane of a neuron and propagation of the action potential. In passive spread, the action potential that gets generated at a site in the membrane of a neuron is going to spread out, and it's going to lose strength as it travels. The propagation form of transmission is very different because during propagation, new action potentials will be generated at certain points along the length of the axon. Let's take a look at this. In this drawing, you're looking at a generic neuron up at the top, and a signal is being received right here at the membrane in one of the dendrites. And we're going to watch that signal as it travels across time and across the distance of the membrane of the neuron. So in comes the signal, whatever it happens to be, and an action potential is generated. This stimulus is big enough to meet threshold potential and generate an action potential. Now, what does that look like? Well, it's going to passively spread out, essentially in all directions from that point. So all of those depolarization, repolarization, hyperpolarization changes we talked about are going to spread across the surface of the membrane. We're not in the cell here, we're on the cell. This is all happening along the length of the membrane, and it's spreading out in all directions. But it's losing strength as it spreads. It's losing strength, and it will sort of peter out. It'll stop, it'll die out. Notice that it's even gone up into this other dendrite and up into this dendrite. It's just passively spreading out. Now, there's a bit of anatomy here that we need to know, and that's this. There is a particular area of membrane at the junction between the nerve cell body and the axon called the axon hillock. If the original action potential spreads out and reaches the hillock, propagation will begin. And that's what they're showing us in this picture. If the stimulus is strong enough and the action potential spreads out enough to hit the hillock, that action potential that was generated here is going to get regenerated right here. That one will then passively spread. It will passively spread in all directions. But if it reaches right here, it's going to get regenerated. As it travels back in this direction, it's just going to peter out. This one is going to spread in all directions. It's going to peter out as it travels back, but it's going to get regenerated right here. It's propagation that sends the signal in one direction, in the direction that it needs to go along the length of the axon. Now, this is a very busy looking diagram, but we'll walk through it together. We're looking at an axon here in yellow, and we're watching what's happening to that axon over time as we go from the top to the bottom of the diagram. So up at the top here, this lighter yellow area represents the inside of the axon, and this darker yellow area represents the membrane, at least on one side. Remember what an axon is. It's just an extension of the cell. The membrane has extended outwards in this long linear pathway. So there's cytoplasm in here, and there's membrane surrounding it. This axon happens to be at rest. There's more negative charge inside relative to the outside. So we're at that minus 60 resting membrane potential. The sodium channels are closed, the potassium channels are closed. We're at rest. The cell body would be up here somewhere with its dendrites. The axon would travel down till it hit the terminal branches over here. Now, something's going to happen. An action potential is going to be generated. And that action potential could have been received through any of the dendrites that extend off the cell body. And it would have passively spread across the membrane until it hit the axon hillock. And what makes the axon hillock unique is that it's loaded with sodium channels. And as long as that originating stimulus is strong enough to bring the membrane to threshold, we're going to get a new action potential generated. And that's what they're showing us here. In the red region of the membrane, sodium channels have opened. Sodium's rushing in. We've generated a new action potential. Notice that it's going to be a passive spread. That sodium rushing in is making the inside of the cell more positive in both directions, right in this region. Passive spread. Now, if the passive spread travels along and hits again another region right here, which happens to be loaded with sodium channels, we're going to generate another one. When this action potential happens right here, passive spread is going to occur. The positives that you see inside the cell, they're going in both directions here, right? So how am I going to prevent this signal from going backwards and hitting the rich region of sodium channels again and send the action potential back to the cell body? How am I going to stop that? Well, I'm going to stop it because there are also potassium channels in this membrane. Don't forget, following depolarization comes repolarization. Potassium channels are going to open. Potassium's going to rush out. Now, we're going to see the inside become more negative again relative to the outside. It's going to passively spread. I'm returning this membrane back down towards resting potential. Meanwhile, the passive spread that's going this way is going to open up more sodium channels. That's going to spread passively forward and backward. But as it travels backward, potassium channels are opening up. So by doing this sequential opening and closing of sodium and potassium channels, and by loading up the axon with sodium channels in very discrete regions along its length, the signal can be sent propagated forward down the length of the axon.